Well, hello everybody. So long you must have a lot of dose about non-ideal solutions, activity coefficients, how to find out activity coefficients, azeotropes, K factors, Van Laar, Margulis, and Wilson, NRT, a lot of things. It's important for you to remember that for the purpose of this particular course, you just need to remember the two suffix modulus equation, and you need to know how to solve problems using the 3 suffix modulus equation and the Van Laar equation. In your assignments and in your test, the basic equations for ln gammas will be provided, and so that you can proceed. But you need to know how to do problems just the way I have done the problems in the last class. Now, before ending the last class, what did I say? I said that it is very important for you to know that when you are dealing with the experimental data, that you are dealing with thermodynamically consistent data. What does thermodynamic consistence of any data mean? It means that the data obeys Gibbs-Duhem equation for any partial molar property or for any partial molar excess property. It is important for you to remember that if any particular thermodynamic data, it does not obey Gibbs-Duhem equation, it is definitely incorrect. But when it obeys Gibbs-Duhem equation, there is no guarantee that it is completely correct. But it can often happen that by a fortunate cancellation of errors, we find that the particular quantity it obeys thermodynamic, or rather it obeys the Gibbs-Duhem equation. Under that condition, we can use the data, it can be considered to be reliable for our thermodynamic purposes, but it is not correct. Such a case is unlikely, but it cannot be ruled out completely. Therefore, we are not dealing with thermodynamic correctness of data, we are just trying to find out how we are going to ensure that the data are thermodynamically consistent. Our main guide is the Gibbs-Duhem equation. What is the Gibbs-Duhem equation? Let us see. All of us, we know that the Gibbs-Duhem equation, it can be written in terms of any particular partial property, where we know this mi bar, this refers to any particular partial molar property for the extensive property M. Now, we know that the same equation can be written in terms of molar, partial molar excess property as well. And we know that this equation, it has got two very important applications which we have already discussed in our previous classes. The first important application is that suppose we do not have the complete thermodynamic data. Then in that case, suppose we have data for suppose we are dealing with C number of components, we have say the activity coefficient for C minus 1 components, we can find out the activity coefficient for the Cth component using the Gibbs-Duhem equation. This we have already discussed. The other important thing is, suppose we have data over the entire range of composition. Then in that case, we can use the data to find out if the experimental data which is available for any particular directly measured partial property, whether it is thermodynamically consistent or not. How do we go about doing this? So, what is the Gibbs-Duhem equation? We have already derived this particular equation, and we know that this is the generalized Gibbs-Duhem equation, right. And usually I have already mentioned that at constant temperature and pressure, this particular term cancels out, this particular term, these two cancels out, and we get this particular equation. And for our practical purpose, we find that mostly we will be dealing with the equation for binary mixture. So, for a binary mixture, under conditions of constant temperature and pressure, the equation reduces to this particular form. Now, and we know therefore that if we have the complete VLE data, what do you mean by the term complete VLE data? It means you have data on P, T, x1 and y1. If you have the complete VLE data, then for a binary system, then we can use this equation to find out whether the data is consistent or not. Now, just by looking at this equation, can you tell me how we can use this equation to find out the thermodynamic data? What is the simplest method? Just by looking at the equation, it is very evident that your x1 d ln gamma 1 by dx1 is equal to x2 d ln gamma 2 by dx2. So, what does it suggest? It suggests that if you are having a plot of say ln gamma 1 versus x1, and if you are having a plot of say ln gamma 2 versus x1, then in that case suppose we are having this particular plot, right. This is 0, this is 1, and at x1 equals to 1, your ln gamma 1 that becomes equal to 0, say suppose, right, and this is say ln gamma 2. So, there is one particular method which is evident from here. You select a number of points here, and once you select a number of points, you can draw tangents and you can find out the slopes at each and every point. For the same compositions, you can find out the slopes of ln gamma 2 versus x2 as well. And then once you can find out the slopes, then you can use this particular equation to find whether the data is thermodynamically consistent or not. This particular technique, it looks to be pretty accurate, and it also appears to be quite simple. At least theoretically it appears to be quite simple. But there are two things which you need to remember. Firstly, finding out slopes in this particular way, it is not very easy, and the second thing is that the experimental data, they will inevitably be having some amount of scatter. So, therefore, it is not so easy and feasible to find out slopes at different particular points very accurately, and then to check up whether the equation, whether this particular equation is going to be valid or not. So, therefore, usually this equation, it is used for some very serious errors in the data. For example, you can just plot ln gamma 1 as a function of x1, ln gamma 2 as a function of x2, and find out whether both the slopes are positive or not. Or else, if you know that ln gamma 1 versus x1 is horizontal at any composition, you can just check that whether at that composition ln gamma 2 versus x1 is horizontal as well. Just these gross checks can be done from this particular slope technique. But in order to check the thermodynamic consistency of data, we find that a better method is the integral area test, or the integral test or the area test, which was proposed by Redlich and Kister and also by Harrington independently. They test the data as a whole. Let us see what this integral or area test is and how it works. So, therefore, for this, what we do, we write down the basic equation which relates molar Gibbs free energy to activity coefficient. What was that particular equation? If you remember, we have been using this equation since the time we have introduced non-ideal solutions. So, for a binary mixture, what happens to this equation? This also we have done a large number of times. If you observe, you will find that for that we do not use a large number of equations, but we use the same equations in different forms to serve our purposes. Like for example, this equation we have been using very frequently, and in different forms, maybe for binary mixtures, for multi-component mixtures we use this. So, for a binary mixture, what do we get? This equation reduces to x1 ln gamma 1 plus x2 ln gamma 2. If we differentiate this particular equation, say with respect to x1, what do we get? We get dGe by RT dx1. This should be equal to ln gamma 1 plus d ln gamma 1 dx1 plus ln gamma 2 dx2 dx1 plus x2 d ln gamma 2 dx1. What is this term? We know dx1 equals to minus dx2. Therefore, this term is nothing but minus 1. So, from here what do we get? We get ln gamma 1 minus ln gamma 2 into dx1 plus x1 dln gamma 1 dx1 plus x2 dln gamma 2 dx2. What is this? This is one of the terms of the Gibbs-Duhem equation. What is this? At constant temperature and pressure, we get that this particular term equals to this. Suppose I write this term as A, then this A term becomes equal to 0, provided we are working at constant temperature under isothermal isobaric conditions. So, therefore, we know that for this particular condition we find dGe by RT dx1, this is dx1 by dx1, this is equals to ln gamma 1 minus ln gamma 2. Or else what can we write this down as? We can write this down as dGe by RT equals to ln gamma 1 by gamma 2 of dx1. Now, we can integrate this particular equation, isn't it? We can integrate this particular equation, say from x1 equals to 0 to x1 equals to 1. Here also we integrate it from x1 equals to 0 to x1 equals to 1. What do we know? We know that at x1 equals to 0 we have pure component x2. So, naturally when we have pure component x2, g by RT becomes equal to 0. At x1 equals to 1, what do we have? We have pure component 1, isn't it? When we have pure component, here we have pure component 2. When we have pure component 1, naturally under that case also g by RT becomes equals to 0. So, therefore, what is the fate of the left hand side of the equation? The left hand side of the equation, when we are integrating it from 0 to 1, this term it disappears off, right. So, therefore, and what about, so therefore, what do we find? We find that x1 equals to 0 to x1 equals to 1, ln gamma 1 by gamma 2 dx1, this should be equal to 0 for gamma 1 and gamma 2 data to be thermodynamically consistent, isn't it? And so, therefore, this is what it is the area test. And remember one thing, we can perform the area test for any particular partial molar property, but the most relevant partial molar property is the partial molar Gibbs free energy, which is given as Gi bar E. This is the most relevant property, and therefore, the Gibbs-Duhem equation expressed in this particular term is most important, since we know that Gi bar E is related to the activity coefficients, and it is very important to find out whether the activity coefficients are thermodynamically consistent or not, and this can be found out if we have gamma 1 and gamma 2 values. Then we can find out ln gamma 1 for each case, we can find out ln gamma 2 for this case, and then we can find out ln gamma 1 by gamma 2 for each case, and then we can plot ln gamma 1 by gamma 2 as a function of x1, and we can more or less we get something of this sort. We find out the area above this, area below this, and then we find whether the areas are equal or not. Accordingly, we can conclude whether the data that we have, it is thermodynamically consistent or not. So, therefore, with this it is quite evident that the basis for testing thermodynamic consistency of VLE data is given by this particular equation. And we also know that we are dealing with experimental data. Now, since we are dealing with experimental data, so therefore, it can always happen that due to experimental uncertainties, we will definitely not get the area to be exactly equal to 0. So, therefore, keeping this in mind, normally it is thought that the area above the x axis minus the area below the x axis divided by the total area has to be less than equal to 2%. So, this is generally the situation which we get. Now, there are certain things, this is till this much is sufficient for your this class, but while you are using some particular technique to find out thermodynamic consistency, it is also important for you to remember the drawbacks of this particular technique. Now, in this particular technique, what do? We have firstly we have assumed constant temperature and pressure. Suppose we do not assume constant temperature and pressure, then the total equation you can, then we actually start with the Gibbs-Duhem equation, which is the then we should be starting with the generalized. Then once we start with the generalized Gibbs-Duhem equation, I will just write down the generalized equation. The actual equation, it should be x1 equals to 0 to x1 equals to 1 ln gamma 1 by gamma 2 dx1. This should be equal to actually He by RT square dt, ranging from the temperature at x1 equals to 0 to the temperature at x1 equals to 1 minus VE by RT dP, where pressure, the corresponding pressure at x1 equals to 1 to x1 equals to 0. This is the generalized equation at constant temperature and pressure, since both these terms they disappear off. So, therefore, we can take this to be equal to 0, but actually this forms the basis of thermodynamic consistency test for VLE data. We know that for isothermal cases, what happens? The first term, it disappears off, right. For isothermal cases, we know that this term should disappear off, and we know that for low pressure cases, this term should disappear off. So, therefore, for isothermal low pressure VLE data, the thermodynamic consistency test is given by gamma 1 by gamma 2 dx1 equals to 0. So, if experimental data satisfy this, then we are happy. But remember one thing, if you are dealing with rigorous testing, then in that case what we should be doing? We should be plotting VE by RT as a function of P, and then we should be finding out the area here. We should also be plotting HE by RT square as a function of T, where T, it ranges from T at x1 equals to 0 to T at x1 equals to 1. Here it should range for P at x1 equals to 0 to P at x1 equals to 1, and then we should be finding out these particular data, and then we should be comparing, and then only we can say that really the data is thermodynamically consistent. But generally what happens, we do not have sufficient data on the excess property of volume and the excess property of He, as a result of which what we do, we generally assume these to be 0, and for the purpose of your undergraduate class, this equation is sufficient for you. Now, when do we have this equal to 0, can you tell me? We have this equal to 0 naturally when your excess volume is 0, in other words the molecules of the two components, they are similar in size. Only under that condition we can have V equals to 0. Can you tell me under what condition we have He equals to 0? Naturally when we mix the two components and there is no enthalpy generation. When will it happen? Firstly, when the two components are chemically similar and there are no azeotrope formation and the boiling points of the components are also close to one another. Under that condition, we are going to have this case, but under all other conditions, it is very difficult to assume this. Particularly, it is important for you to remember that when we are dealing with gamma 1 by gamma 2, actually what are we doing? You just try to understand. This is given by x1 f10 by phi 1 phi 2 v y 2 by x2 f20. So, therefore, what are we doing? We are actually cancelling out the pressure term, and that is the term which is very important because that can be measured very accurately and it is very it can it's very easy to know the total pressure conditions. So therefore, when we are doing this area test, we are actually cancelling out the pressure term, and that is the main limitation of this test. And therefore, if you have to do it accurately, the way I was telling, we have 3 data. We have, for isothermal data, we can vary p, x, y. We should be generating data on p, x, y and on p, y as well as on p, x, and then we from the 2 data we should be finding out the third, compare that with the experimental value. Only under that condition we will be convinced that the data are thermodynamically consistent. But for your purpose, it is sufficient for you to remember that if you plot ln gamma 1 by gamma 2 versus x1 and find the area to be 0, your purpose is served. You can say that the data is thermodynamically consistent. If you recall that we have done a large number of problems in the last class regarding generating pxy data, txy data, etc., etc. Now, it is very important for you to test whether those data were thermodynamically consistent or not. So, we are taking up one particular problem from this set of problems that we had. If you remember that in this particular problem you had already calculated gamma 1, gamma 2, and so therefore, from this particular data it is very easy for you to calculate ln gamma 1 by gamma 2, right. So, I will just very short, I will be writing down the corresponding ln gamma 1 by gamma 2 in this particular case. If you remember, the data was 0.297, yeah, 0.447, 0.5650, 0.65. I am going to write a good number of data so that you can check up whether you had done it correctly or not. X1 0.926, 0.945. The corresponding ln gamma 1 by gamma 2, gamma 1 and gamma 2 we had already calculated in the last class. So, therefore, you can calculate this 2, 2, 3, 4. This was minus 0.415, minus 0.2245, then it was minus 0.3496, minus 0.4668, minus 0.6396. This was minus 0.6908 and minus 0.7056. So, with these what you can do, you can plot ln gamma 1 by gamma 2 versus x1, right. And we find that in this case the area above the x axis, this particular portion, this area it corresponds to 1760, whereas this part of the area it corresponds to 2340 as is written. So, therefore, if you subject it to the criteria that we had, that area above x minus area x divided by the total area, then we find that in this particular case your a minus b by a plus b, this gives you as 0.1415, which is definitely greater than 0.02. So, with this what do you conclude? You find out that in this case the data is not thermodynamically consistent. We had wasted a good amount of time in finding out the data and in using the 2 suffix modulus and the Van Laar equation, but in reality the data was not thermodynamically consistent. At least from the fragmentary thing that you have done, it appears that it is not thermodynamically consistent, but it is very difficult for us to conclude it in such a simple fashion, because for this particular case you are required to find out in this case the He by RT square, right, He dt by RT square, just as I had said, and this has to be found out, and this has to be, it's required to verify whether this is equal to 0 or not. If we find that this equal to 0, then only we can conclusively say that the area test or it shows that the data is not thermodynamically consistent, otherwise it is very difficult for us to predict this. And so, therefore, this possibly highlights the limitations of the the area test to test the thermodynamic consistency of data. And it is important for us to remember that the assumptions of excess volume energy of mixing as well as the excess enthalpy change of mixing is also always not very accurate, right. But anyhow, it is very important for us to remember that even though ln gamma 1 by gamma 2 as an area test has got some limitations, there are some very important applications or rather some very important implications of this particular term ln gamma 1 by gamma 2. Let us see what are the what are the interesting things which this particular term ln gamma 1 by gamma 2 has. We find that this is a very effective parameter in defining the different types of mixtures into simple, more complex and most complex solutions. How? Suppose we plot ln gamma 1 by gamma 2 as a function of x1, we find that suppose for simple mixtures like say hexane and toluene in this particular case, we find that it is more or less a straight line, and we immediately say that this particular solution at the pressure condition it is straight line. On the other hand, suppose we plot the log gamma 1 by gamma 2 versus x1 for benzene isooctane, we find that in this case it is curved. It is interesting to note that for both the cases we have been dealing with one particular aliphatic hydrocarbon and one particular aromatic hydrocarbon. Despite that, we found that in this case we had obtained a linear curve, in this case we had obtained a curved solution, and this can be attributed to the difference in the sizes of the molecules constituting benzene and isooctane and hexane and toluene. While the molecules are similar in size, while for hexane and toluene there is much difference between the sizes for benzene and isooctane. So, although we are dealing with similar type of components, we find that the graphs of log gamma 1 by gamma 2 versus x1 are not the same. While hexane toluene conforms to simple solutions, we find that benzene isotoluene it does not conform to simple solutions under this particular pressure condition. And interestingly, when we go for some other mixtures, we find that it is not only that it is curved, there is also a point of inflection. For example, in the case of ethanol and methyl cyclohexane. Now what does this complexity imply? From the graphs, when we know that this equation is simple, this is more complex, this is most complex, how do we use this information? We use this information, if you recollect that we had referred to the Redlich-Kister equation, which was an extension of the 2 suffix Margulis equation. It simply added more number of terms, and by that we could have a much more realistic expression or equation to express d by RT as a function of compositions. Now, from this equation we find that we can find out ln gamma 1 by gamma 2, and from there we can find out ln gamma 1 by gamma 2. So, if we compare this expression as well as the graphs here, what do we see? If we compare this particular equation as well as the curves here, we find that for the curve, for the first curve, it is sufficient to use just one particular term in ln gamma 1 by gamma 2. So, therefore, the first curve represents those solutions which can be accurately predicted by 2 suffix Margulis equation. For the second case, we find that for this particular case we have to include the first and the second case, for this first and the second terms, and we find for that for the last case, which is the most complex or highly complex mixture, an accurate prediction can be obtained if we include the first 4 terms in this case. So, therefore, we find that log gamma 1 by gamma 2 has got a good amount of rather it has got a very good amount of importance in classifying mixtures as simple, more complex and most complex. But at the same time, it is important to remember that this classification is more or less arbitrary, because there can be solutions which may, due to fortunate cancellation of errors again, which may be predicted by 1 or 2 parameters, but actually in reality they are much more complex. A typical example of this is the mixture of 2 alcohols, say methanol and ethanol. We find that very frequently they can be well predicted by just using 1 or 2 parameters of the Redlich-Kister equation, but in reality they are much more complex due to hydrogen bonding. Another very interesting example we can find in the case of acetic acid and water. If you observe the excess Gibbs free energy curve as a function of composition, you find that it resembles the 2 parameter Margulis equation. Therefore, you will be tempted to say that acetic acid water, it forms a simple solution. But when you compare the HE curve and the TSE curve, immediately it shows that in reality it is a complex mixture, and the similarity of the excess Gibbs free energy curve with the 2 suffix Margulis equation is obtained just due to a fortunate cancellation of errors. So, therefore, with this I conclude this class, and before ending I would like to mention that most of the solutions that we deal in chemical engineering, solutions of non-electrolytes, they can very well be predicted by including 2 to 3 parameters in the Redlich-Kister equation. So, therefore, most of them they are solutions of intermediate complexity. So, with that I would like to emphasize that we had discussed the area test for discussing thermodynamic consistency of experimental data, and I had also discussed the limitations of the area test. It is very important to remember that it is applicable only when your gamma 1, gamma 2, they do not vary remarkably with temperature and pressure. And for most of the cases, for much more rigorous testing, we need to calculate, or rather we need to consider the excess volume change and the excess enthalpy change of mixing of the solutions. And apart from that, I also discussed the other importance of log gamma 1 by gamma 2, this particular parameter. It is not only used for finding out the thermodynamic consistency of data, it is also used for classifying data, rather classifying solutions as simple, complex and more complex, and they give us an idea of regarding the number of parameters of the Redlich-Kister equation which should be included in order to predict the VLE data of that particular mixture. And again I would like to emphasize that this is quite arbitrary, although it is generally used, it is quite arbitrary, and for several particular solutions like say acetic acid water, methanol, ethanol, etc., it can give some misleading results due to a fortunate cancellation of errors. Now, with this we are going to finish our topics of solutions, both ideal and non-ideal. So far we have been dealing with completely miscible systems. We are going to discuss some more interesting aspects of VLE in the next class. Thank you very much.